Okay, today we are going to introduce the first concept in multi-user information theory. Multi-user because we are considering problems that include more than one transmitter and one receiver. So the goal is to introduce the case of two users, multi-access channel, denoted as MAC, MAC. We will treat the Gaussian case. We extend the results to the case of K users, the generic case. And then we are going to look at the structure of the capacity region of this channel and some resource allocation problems that can be cast as convex optimization problems and therefore can be solved efficiently using a particular structure that is called the polymatroid structure. Okay, the model for a discrete memoryless two-user multi-access channel consists of two transmitters. Each transmitter wants to deliver an information message to a common receiver. So W1 and W2 are two information messages selected independently with uniform probability over their own message set. The transmitters can drive the channel with two inputs, x1, x2, and the channel has one output y, so the transition probability is p of y given x1, x2. The receiver will decode the sequence of received output y and produce an estimate of the two messages. So these models, for example, the case where we have two phones and we have here a wireless router or a base station, so something like this, and therefore we have transmission, so-called uplink of a system like that, where the two phones typically coordinate according to some multi-access protocol in order to align the transmission, do something such that the interference here is not too harmful. But here, in fact, this problem does not have interference. Why? Because in information theory, interference is when some receiver suffers from the presence of messages that he doesn't want. But this receiver wants both messages. So there is no interference because both messages are wanted. So the receiver can do joint decoding of the two messages. And so the reason why in networking we talk about multi-access interference and the acronym MAC is used to denote something different. It's used to denote medium access control, and there are all these protocols, like for example Aloha, CSMA, so the collision, carrier sense multiple access, TDMA, FDMA, all these say, in a certain sense, a little bit heuristic ways of avoiding interference at the common receiver, the matter of the fact that none of these is really needed when you consider the problem from a fundamental viewpoint. So this is what is written here. The networking approach to the MAC is to try to avoid multi-user interference, and this can be done through a lot of protocols. It can be done through signal design, for example, in the case of code division multiple access or ultra-wideband communication. You try to somehow create signals that interfere very little with each other. But in fact, as I say, this is a little bit of a heuristic approach. So we want to consider the problem from a more fundamental viewpoint. So we define our problem as a discrete memoryless MAC with two users. So we have two alphabets, x1, x2, transition probability matrix, P of y given x1, x2, and an output alphabet y. We have the code, a MAC code that is formed by two message sets. So M1 contains the messages for user 1 from 1 to 2 to the n R1. M2 contains the messages for user 2, again indices from 1 to 2 to the n R2. So R1 and R2 are the rates of user 1 and user 2 in bit per channel use or bit per symbol. We have two encoding functions that maps messages into code words. Code words are sequences. For user 1 are sequences over the alphabet x1. For user 2 are sequences over the alphabet x2. And we have a decoding function. A decoding function is a map that maps sequences of the output into pairs of messages and therefore a decision on the transmitted messages. And we can define the probability of error for such a code as the probability that the two decoded messages are different from the transmitted ones. And basically, we consider that two messages, M1 and M2, are independent and uniformly distributed over their message sets. And we can define the capacity region of the MAC as the set of all pairs of rates, R1, R2, for which there exists a sequence of codes of rate to R1, R2, such that the probability of error becomes arbitrarily small, so it vanishes to 0 as n goes to infinity. So why we talk about capacity region instead of just the capacity? Because now we have two users, so we have two rates, and therefore there will be a rate R1 and a rate R2, and you may imagine that there is some sort of trade-off between these two rates. If you want to operate at a point where R1 is very large, maybe R2 cannot be very large. So the region, we expect the region would be something like this, such that all the pairs inside this region are feasible, so they or achievable. So according to this definition, there exists sequence of codes with vanishing probability of error operating at rate points inside this region, while if I want to pick a rate point here that is outside the region, then I cannot find such codes. Okay? So in general, in multi-user problems where we have more than one message set, we have always this trade-off between different rates, and we want to define a capacity region, which is the region of rates that are achievable by the system. So let's start with the simple inner and outer bounds to the capacity region. Well, first of all, the simple inner bound is time sharing. In time sharing, basically we divide the time into slots, right? This is time. And we allocate one slot to user 1 and one slot to user 2, according to some fraction of time. So it's some duty cycle. It need not be 50% or 50%. You can dedicate a fraction of lambda to user 1 and 1 minus lambda to user 2. So what happens when user 1 transmits? When user 1 transmits, we have, in fact, a single user channel, very traditional single user channel, right? Because basically we have only the path from user 1 to y. However, this distribution depends also on x2. So while user 1 transmits, according to this protocol, user 2 can help as much as he can by simply picking the symbol, a particular symbol in X2 that maximize the mutual information between X1 and Y. For example, if we are talking about an additive channel for which the symbols add on the real line, the best thing for user 2 is to transmit 0. Well, that's obvious, right? In transmit 0, you don't create disturbances. But notice that the symbol for user 2 cannot depend on the message of user 1. Otherwise, this would be that, it would be like a hidden channel here, and this cooperation is prohibited by the assumption of the MAC channel. The two message set must be independent, which makes the two code words independent. Okay, so in general, for memoryless, discrete memoryless channel, well, 0 is not a well-defined concept. It doesn't mean that 0 is the most helpful symbol. So essentially, what we can write is that the capacity for user 1 is going to be the max of the mutual information over the input probability of user 1 and the symbol alphabet of user 2 of the mutual information between X1 and Y when X2 is fixed to a particular symbol, which is the most helpful symbol for user 1. Same thing for user 2, the capacity for user 2 when user 2 is alone in, say, phase 2 of the protocol, of the time-sharing protocol, then user 2 will be able to transmit at capacity, which is the maximum of the mutual information when the maximization is over px2 and a symbol in the alphabet x1 of the mutual information y, x2y given x1 fixed to the most helpful symbol for user 2. And then if you consider all the region you can construct in this way, so we have again our rate, well, there will be some number here which I call C1, which is given by this. Some other number here need not be the same because the two users may not be symmetric, that is C2. And then when I consider all possible time sharing fraction of time lambda, I obtain basically the straight line, which is the convex combination between these 2 points. So the TDMA region is this triangle, which analytically can be written as all the rates R1, R2 that satisfies this inequality. Okay, that's the time sharing region. Then there is an upper bound, which simply say, okay, let's allow the two users to cooperate. So now the two users will act as a single transmitter that conveys the Cartesian product of the messages M1 M2. So this bounds the sum rate because overall the Cartesian product of the messages contains 2 to the n R1 times 2 to the n R2 total messages. So if I take 1 over n logarithm of this, I find R1 plus R2, so it's the rate sum. And this is less or equal to what? To the maximum of the mutual information between the pairs x1, x2, and y, because x1, x2 now act as a single input. The only caveat here to make the bound as tight as possible is that the maximization, since we know that x1, x2 have to be picked independently, the maximization is over all possible product distributions. Product distribution, not joint distribution. So in other words, we maximize over the product distribution px1, px2, which is a subset of all the possible joint distribution px1, x2. So you see that the product distribution means that x1, x2 must be independent, while in general, if I can choose over all possible distribution of x1, x2, I have a larger set. So this maximization is restricted to product distribution because by definition of the problem, I want to repeat once more, the two messages are independent and therefore the two inputs here must be independent. Okay? So this gives us a bound on the rate sum. So there is like a straight line here with slope -1. And we know that the region R1 plus R2 less than this quantity is basically this big triangle. Okay, so the picture is this, and we have this. This is the bound on the sum rate, and these are the individual capacities of the two users, and we have the TDMA inner bound is this triangle, and then we have this outer bound, which is this other line. And therefore, the capacity region is anything in between here, is some boundary in between here, okay? Now, from a time-sharing argument, we can immediately argue that this capacity region must be a convex region. Why is that? Well, imagine the following. Suppose that, let me clean up this picture for a second. Suppose that a point here is achievable. So suppose that I can find a family of codes that with vanishing probability of error that operates at this rate pair. Then suppose that another point here is achievable. Okay, fine. So you see immediately then, if I find a point that is achievable, all the rate pairs that are component-wise dominated by this point are also achievable by definition of achievability. Then it means that, okay, I have constructed a strange capacity region like this, which is non-convex, okay? But now I can say, okay, but now I can do time sharing between the code that achieved this point and the code that achieved the other point, and then I immediately find that the convex combination between these 2 points is also achievable, and therefore all these points are achievable, which means that since I can repeat this reasoning over and over, it means that the capacity region is always given by the convex hull of all the achievable points, which of course is convex. Okay, so this is true whenever we can use time sharing. There are some problems in which time sharing is forbidden by assumption of the problem, but in general, if you have two strategies, you can always decide to use one strategy for a certain fraction lambda of the time, another strategy for a fraction 1 minus lambda, and then you can vary lambda and achieve all the points in the convex combination. Okay, so the region is convex, so it's like a potato like this, limited by the two axes. And now we want to discover how this region looks like. And here is the theorem that says that the Mach capacity region for two users is given by the union over all possible distributions of the type P sub Q, Px1 given Q, Px2 given Q of the rate pairs satisfying these three inequalities. Okay? And in addition, what is Q? Well, Q is called an auxiliary random variable, and we will see that in multi-user information theory, many results are given in terms of auxiliary random variables that do not appear directly into the problem definition from the beginning. You see, the problem definition contains only x1, x2, and y. The random variable relevant here are x1, x2, and y. But in this case, the capacity region is expressed in terms of x1, x2, and y, of course, but also in terms of this q, which is a random variable that does not appear in the problem definition. It's called an auxiliary random variable. We will see how it comes about. And of course, this region would be uncomputable if we do not know the alphabet of Q. because in order to do this optimization, we need, this becomes a finite dimensional optimization only if these probabilities are probability vectors on a given dimension and probability matrices of a certain dimension. So we know the size of the alphabets x1, x2, and y, so everything is finite dimensional. We are talking about a standard discrete memoryless channel, but if we do not have a bound on the cardinality of the alphabet Q, this quantity, this region is uncomputable because we do not know where to optimize from, so where to take the union over, okay? So it is essential in this type of results also have what is called a cardinality bound on the alphabet of the random variables that do not appear directly into the problem. In this case, it turns out that Q has an alphabet of cardinality at most 3. That's okay. So just to give you an example of this region, suppose for a second that we fix a given distribution. So we fix a certain, say, Q equal to small q fixed, and therefore we pick two input distribution, say px1 given q equal to small q and px2 given q equal to small q. Okay, so those are fixed input distributions. Okay, and then we just evaluate, say, plot the set of inequalities that we have here. So we have two individual rate inequality, an inequality for R1, inequality for R2, and one that determines the rate sum. So this gives us R1 less than the mutual information between x1 and y given x2, and of course q is fixed, so it doesn't even appear, which will be this boundary. Then we have a bound on R2, which gives this boundary, and then we have a bound on the sum that gives us this boundary. And by using the chain rule, you see these 2 points are called the corner point or vertices of this region. You see, by using the chain rule, if, for example, this point is the point at which R1 is equal to the sum, which is I x1, I x1 comma x2 y minus R2, which is I x2 y given x1, and by using the chain rule here, so breaking up this mutual information x1, x2 given, and y into x1 and y plus x2 y given x1, that simplifies with this term with the minus, we find that this is simply the mutual information between x1 and y. Okay, so we have this point. And similarly, the other corner point, by the same reasoning as changing the role of x1, x2, gives you this. So these corner points are particularly interesting, and we will see later, we'll make a comment on why they are particularly interesting. Okay? So you see, this sort of strange pentagon is what we find, is the region we find for fixed choice of 2 input distributions. Now, imagine that we repeat this for many other choices of Q. Every time Q changes, we find a new pentagon. So maybe for another value of Q, we find something like this. For another value of Q, we find something like this. For another one, we find something like this. So imagine we have all these pentagons, and at the end, altogether, what we take the union over all these things, effectively what we are going to have is precisely like a convex combination of all these pentagons. So we get a region that may look like this. Okay. Good. So now we want to prove this theorem. So the proof, as usual, goes through two steps. The first step is proving achievability, and the second step consists of proving a converse. Achievability, we simply fix a particular choice of P sub Q, Px1 given Q, Px2 given Q, and we shall show that the points inside the pentagon corresponding to this choice, I say that for every choice of these distributions we have a region that looks like a pentagon. I call this region R of x1, x2, and q because it depends on a fixed choice of these distributions. Okay, so we shall show that any point inside this region is achievable. So there exist codes with vanishing probability of error. And of course, this concludes the proof because the remaining part of the proof is simply the completion, taking like the union over all possibilities and taking the convex solve of this, right? So this is what we end up with. So how do we show achievability? We use an idea, the same idea that we have already used for proving the capacity of a single user channel. So we do random coding. So we generate a random code as follows. First, we generate a typical sequence Q of length n. Typical with respect to what? Well, with respect to the PMF P sub Q that we have chosen. Okay. For this typical Q, we generate two independent code books. One consists of 2 to the nr1 code words x1. The other one consists of 2 to the nr2 code words x2. And how we generate these code books? Well, we simply generate remember, a code book is always a table. A table with n columns and 2 to the n, in this case r1, and then we have another one that will have n columns and maybe 2 to the n r2 rows. Every row is generated at random according to some distributions. And which distribution we use here? Well, to generate, imagine, I change color so you see it better. To generate the ith letter of every code word here, I use the distribution P sub x1 given Q for the ith letter of that sequence that we have chosen. And the same thing for the I letter of codebook 2, we use this distribution. Okay? So in other words, the sequence Q acts as a sequence of seeds of random number generators, and we use the ith seed to generate the ith letter of each code word. Okay? Good. So the encoding is trivial. In order to send the message M1, encoder 1 transmits simply the M1th row of its own codebook table. Similarly, for encoder 2 transmits the M2 row of the table. These codewords are transmitted one symbol at a time, and the symbols go simultaneously into the channel because the channel has, remember, two inputs and one output, x1, x2, y. So we feed the code words here sequentially, okay? And the receiver receives a sequence that it will be yn is the sequence of received symbols at the output. So with an argument that you can work out by yourself that is completely analogous to the argument that we have used in the proof of the channel coding theorem for a single user channel, we can consider the ensemble average error probability, which is denoted as P with this overline that denotes ensemble average. What is ensemble average? Remember, ensemble average means average over also the choice, the generation of the random codebook. So it's not only average error probability for a given code, is average over all possible random codes. And then this ensemble average error probability turns out to be independent of the particular messages that we have selected, precisely because by generating the code words in an independent fashion, we can permute all the code words, which corresponds to permute all the messages, and we still find the same code book. So in other words, the identity of the transmitted messages is irrelevant. We can study, so the problem becomes symmetrized with respect to the messages. We can consider that without loss of generality, the two transmitted messages are message 1, 1, and therefore the probability of error is the probability that the decoder chooses something that is not 1, 1. And so it's important to consider the joint probability distribution of sequence Q, code word for message 1, code word for message 2, and Y in all the possible cases, because when M1 and 2 are 1, 1, so the transmitted messages, it turns out that the joint distribution of these vectors goes as follows. We have px1 given q, px2 given q, py given x1, x2, because y is the output generated by x1, x2. So we have, let's say, the correct joint probability structure of x1, x2, and y. When message 2 is 1, but message 1 is anything different from 1, so star means a generic message different from 1, it means that we are looking, imagine we have our code books, so we are considering now the first row, which is the code word, the transmitted code for x2. The first row is the transmitted code of x1. These two generate y. And then we have another row of this array, which corresponds to the message star, that has nothing to do with the first row. In fact, it's independent, which means that in this case, we have that x2 and y are generated, follow let's say the joint distribution between x2 and y, but x1, when we look at a different row, is distributed independently. So you see that here the x1, here the conditioning is missing. Similarly, for the case 1 star, we have that x1 and y are jointly distributed, but x2 is independent. And finally, when we have star star, then we have that x1, x2, and y are independent, because y is generated by the first row, and now we are looking at two generic other rows of the two arrays, which are independent, of course, on whatever happens here. Okay. So this sort of joint probability model for the random vectors, let's say, induced by this random codebook generation and averaging over all possible codebooks is very important, because now we consider the joint typicality decoder. So how the decoder works: the decoder declares messages m1 hat, m2 hat, if this is the unique index pair such that there exist two code words and the received output that are jointly typical given the fixed sequence Q. So this is the jointly typical set of x1, x2, and y given typical sequence Q. Otherwise, we declare an error, or otherwise we choose arbitrarily some fixed messages. So the decoder checks these joint typicality conditions. That's very similar to what we have seen for the single user case. So now what we have to do is to consider the error event, so the event that the decoder misses the correct pair of messages, and this error event E is in a subset of the union between an event E0. E0 is the event that Q is non-typical. Okay, so the sequence Q is non-typical, then everything collapses. But so we count this as error, and then we have the another event, which is in fact the intersection of the complement of E0, which is Q is typical, intersect with the union of four other events, where events E1 is the event that the transmitted code words and the corresponding output are not jointly typical. E2 is the event that there exists some other message M1 different from 1. So this is the star that in this table, such that there is another triple of vectors, so x1, m1, x2, 1, and y, that are jointly typical. So in this case, then, 1, 1 is not the unique choice, because there is also m1, 1. And so the decoder makes a mistake. Then we have E3, which is similar. There is some message M2 different from 1, from which x11, x2, m2, and y are jointly typical. And finally, E4, when there exists some m1 and m2 different from 1, 1, for which this triple is jointly typical. Remember one thing, that for some means union, so these events are these events can be written as union over all m1 different from 1 of blah blah, or union over all m2 different from 1 or the same of the event, and then union over all m1 and 2 different from 1 of, actually I should have written not like this, because union over the pairs m1 and 2 different from 1, 1, which is different from what I wrote, because this means that both are different from 1, 1 of the event, right? So every time you read a for some, you have to think this is a union over all possibilities. Okay. And for all is the intersection. For all means that the condition must be true for all, so it's the intersection of conditions. For some is the event is verified if at least one, so at least one means union. Okay, just to make sure. So now we can go a little bit fast because the mechanism is quite clear. You will see that sometimes it's actually quite repetitive the way this proof develops. So first of all, let's analyze where we use the union bound. So we want to bound the probability of this error, so we bound it as the sum of the probabilities of this guy and then and this one. And these you can also so basically we have probability of P0 plus probability of E0C intersect E1 plus probability of E0C intersect E2, etc. And this is the union bound. So we can take these one at a time, and if we can prove that they all go to zero, then we have proven that the probability of error and averaged over the random code generation goes to zero, and therefore with the usual argument that if the average probability of error over all possible codes goes to zero, there must be a deterministic sequence of codes that does at least as good as average, which means for which we have proved the existence of such codes with probability of error that vanishes as the block length goes to infinity. So the probability that of E0 goes to zero. Why? Because Q is generated according to the distribution PQ, and the probability of the typical set goes to 1, so the probability of the randomly generated Q is non-typical goes to 0, and so this is just the law of large numbers. Then we use the conditional typicality lemma that says, okay, if we generate Q is typical and we generate x1, x2, and x1, x2, and y. X1, x2 are generated according to the correct probability. Y is the output corresponding to x11, x12. So basically x1, x2, and y follow the correct joint distribution of everything. Then the probability that this triple is non-typical here also vanishes. And this is the conditional typicality lemma because we use the conditioning with respect to Q, and this settles that one. The other three events contain a union over many possibilities, and therefore we use the packing lemma. So basically, you will recognize that this is exactly the statement of the packing lemma in every case. So we have, for example, that take for example, here is so here is the summary of the results. So here we have the final inequality that we are going to have. Now I'm going to pick one case and see how this inequality is derived. So for example, let's consider the bound for E2 intersection E0C. So it is this one. So by definition, we have that because we are intersecting with E0C, then the sequence Q is any epsilon prime typical fixed sequence, and therefore we have the following thing is that probability of this event is the event that there exists a sequence x1 m1 which is independently distributed with respect to x2 and y, because m1 is different from 1, and they are jointly typical with respect to the typical set of x1, x2. Here I have forgotten y. Oopsie. Given q for some m1. Now I use, for some means union, so I use the union bound. So I sum over all possible messages m1 different from 1, and here I have the probability that this sequence, so this triple is jointly typical, but this triple has the property that this guy here, x1, is independent on x2 and y. And we know that the probability that two long sequences that are independently distributed according to the marginal probabilities are jointly typical goes exponentially to 0. So this term here goes like, and this is the joint typicality lemma, goes to 0 as 2 to the minus n times the mutual information between the two objects. And the two objects are x1 on one side and x2y on the other side. And then the given q, because we are considering this conditional typical lemma given the sequence q. So this is just a joint typicality lemma. But here we have the sum that gives us this term. This is the number of terms in the sum. In fact, this is the number of terms of the sum plus 1, because we are considering all the messages but the message 1. But since we are after an upper bound, the plus 1 is totally irrelevant, and therefore we just use 2 to the n r1. So the result is that we have that this is 2 to the minus n, and then we have the mutual information x1, x2y given q minus a little delta minus r1. So this whole thing goes to 0 if this difference remains positive, and therefore we get a bound for rate r1. The only thing is that this mutual information x1 and x2y is not what I have written here. We want x1y given x2. So there is one little extra step that says, okay, now I have this mutual information, and now I can write it using the chain rule as the mutual information between x1 and x2 given q plus mutual information between x1 and y given x2 and q. This is just the chain rule. And we recognize that by construction, x1 and x2 given q are independent, because we have generated x1 and x2 given q independently. So this mutual information is 0, and so effectively the mutual information that really matters is exactly what is written here. Okay. Now you can repeat the same reasoning for B and C. For B, just invert the role of x1 and x2. For C, it follows very, very similar steps. The only thing is now you are summing over all pairs m1 and 2 different from 1, 1. And basically, you are going to, at the end here, have an inequality where the sum contains, is a double sum, so it contains the number of terms, which is going to be like this, and the probability, the joint typicality lemma give us the probability of this kind. It will be the mutual information between x1 and x2, because you say in this case we have that for m1 and 2 different from 1, 1, we are in this case where x1, x2, and y are independent. So the probability that they are jointly typical is going to be like this, with 2 to the minus n times mutual information minus a small delta. Okay. So this is for the last inequality. Okay. So this basically proves the result because through the random coding argument, we have that we have proven that as long as the so here the rate R1 is less than the mutual information X1 and Y given X2 Q minus a small delta R2 is less than the mutual information X2Y X1 Q minus delta epsilon and R1 plus R2 is less than mutual information X1, X2, and Y given Q minus delta. As long as this is true, then the ensemble probability of error, ensemble average probability of error goes to 0, and this proves the existence of deterministic sequences of codes for which we conclude these rates are achievable, and then you can go as close as you want to the boundary, and when you take the closure, you get the inequality with the less or equal, and so we have proven that any point in the interior of that pentagon is achievable. Okay, so now we want also to prove the converse, and the converse goes as follows. First of all, we assume that we are given a sequence of codes of rate R1, R2, and increase in block length n, such that as we increase n, the probability of error goes to 0. And we want to prove that if such sequence of code exists, then R1, R2 must be inside the region we have given in the theorem, which automatically implies that no codes with vanishing probability of error exist for rate pairs outside that region. So we have to look, in the converses, we always look at the joint probability distribution, so-called multi-letter probability distribution, induced on the sequences of length n at the input and output of the channel, induced by the code which is given to us, and we cannot assume anything apart from the fact that the probability of error vanishes, and the independent and uniformly distributed choice of the messages. So we look at the joint probability distribution between the messages, which are independent uniform random variables. Then these two sequences are the corresponding code words, and this is the corresponding output of the channel. So this joint probability distribution, we know, is, first of all, is the probability distribution of M1, M2, which is uniform, so it's 1 over the size of the Cartesian product of M1, M2. Then we have simply indicator function that say X1 is the code word corresponding to message M1, and X2 is a code word corresponding to message M2. So this is just like a trivial probability mass function that put mass 1 at the code word corresponding to the transmitted message and 0 everywhere else. And then we have the channel, which is memoryless, so the Y given X1, X2 is distributed according to this product distribution, where here we have the letter, the ith letter, and here we have the corresponding two inputs. Okay, so that's the joint probability distribution over the n-letter problem. So now we start with fun inequality, because we have to look at basically we want to, so the decoder makes decisions on M1, M2 based on Y. So we apply fun inequality to this inference problem, so we can bound the conditional entropy of what we want to decide upon, which is M1, M2, given our observation is less or equal than 1 plus the log of the size of the possibilities, so in this case n R1 plus R2 times the probability of error. And if we collect n in front, we have n 1 over n plus R1, R2 are just two constants. And then we have PE of n. PE of n goes to 0. So the whole thing can be written as n times epsilon n, where this quantity is epsilon n and vanishes as n goes to infinity. Okay. Similarly, we can consider also what happened. I don't know. We can consider also these conditional entropies, where we consider the entropy of M1 given y n and M2, and M2 given ym and M1. Of course, these entropies are less or equal than this other conditional entropy. This is easy it can immediately be seen from the chain rule and the non-negativity of entropy. So if this term is less than n epsilon n, it's also true that these two are less than n epsilon n. Okay. So at this point, we can simply, by very simple adding and subtracting, we can write the following. N times R1, R2 is the joint entropy of M1, M2, because they are uniformly distributed over their message sets and they are independent. Then I subtract and add this conditional entropy such that eventually this term is very small, so it is smaller than n epsilon n, and this difference gives me this mutual information. Okay, so I end up with this bound, and I can do similar thing here for the individual rate by adding and subtracting these other conditional entropies. And why I can write nr1 as this conditional entropy here, because the two messages are independent. So we have that h m1 given m2, in fact, is h over m1. But I like to write it in this form because then I have that the difference between these two terms is simply these mutual informations. And now you see that these mutual informations reflect more or less what we want to get at the end. And we have, M1, M2, and Y, M1 and Y given M2, M2 and Y given M1. While at the end, the result we want to prove contains the mutual informations where the M are replaced by X's. Okay. And there is also a fundamental difference here. The difference is that those are so-called single letter expression. You see there is no vectors of length n appearing here, but here we have multi-letter expressions. You see, this depends on n. So now we want to do something called single letterization, which is basically using whatever artifacts we know, information theoretic inequalities and identities, to break these mutual informations and somehow get to the point where we get single letter expressions and hopefully expressions that coincide with what we have just proved to be achievable. And this concludes the result. So let's see how it works with the sum rate inequality. This first, the other two follow exactly the same way. So it's really not worthwhile to repeat everything. For the sum rate inequality, so this is our starting point, this inequality, then we can break this mutual information using the chain rule with respect to the y vector. So you see, this is the chain rule. Then what we can do is to notice that the letters, the ith letters for x1, x2 are a function of m1, m2, because x1, x2 are the code words corresponding to messages m1, m2 and a given code which is given to us. So we can introduce them here because basically they are just the functions of m1 and 2. So in a certain sense they are already connected. They will not change the mutual information. Then what we can do, we can recognize that well, we can use the chain rule basically and write this mutual information as the mutual information between x1i, x2i, and yi given the past of I from 1 to I minus 1 here, plus everything else, right? And now these two terms go into the condition. So this is just the chain rule by breaking first these two and then these two, okay? And then we recognize one fundamental thing is that the channel is memoryless, which means that if I fix x1 at time I and x2 at time I, then y at time I is independent on everything else, is independent on the messages and independent on the past of y. This is a condition of memoryless. When you fix the input, basically the output becomes independent on everything else. So given this conditioning, then yi becomes independent of m1, m2, and this conditioning becomes irrelevant, so this mutual information is 0. And so we end up with simply this thing here, and also this conditioning becomes irrelevant because we have basically just these two, and that's easy to see. So we, or if you don't want to see it, you can write these in this following way. This mutual information can be written as the entropy of y I given I minus 1 minus entropy of yi given x1i, x2i, and yi minus 1. So what happens is that what we can do is that we can neglect these and we get an upper bound, and then this term disappears because we will condition on these two. x1i, x2i, yi is independent on the past of y, and so okay, this is maybe an upper bound. But we are going to, as long as we maintain the chain of inequality, everything is fine. Because at the end we want to prove that R1, R2 are less than something. Okay? Good. So basically, yeah, so the individual rate, okay, here I give you also the development for one individual rate. They work in a very similar way. So at the end, we end up with the following three inequalities. So if I collect, the last line here, and the last line here, and also the other one, exchanging the role of the 1 and 2, I get the other inequality. I end up with these inequalities, which is already a step forward because the messages have disappeared, but they're still multi-letter expressions. Simply now they are broken into single letter, in sum of single letter expressions, but you see the I here. So these mutual informations are with respect to the ith marginals of x1, x2, and y induced by the big multi-letter distribution. So we cannot say that these do not depend on I. It's not true. It depends on the code, and we cannot make any assumption on the code because it's given to us. Okay. So at this point, once we have broken the multi-letter expression into this sum, the last step is to go from multi-letter to single letter is to introduce it's called a time-sharing argument, which simply does the following. We define a new random variable. How many typos? Variable. Not variance, variable. And this random variable, I call it Q, and it is uniform from 1 to n. So basically, you recognize that written in this way, this sum of mutual information with sort of this empirical mean of mutual information, 1 over n, sum of all the mutual information, is in fact the conditional mutual information written in this way, where Q is uniform from 1 to n. because that's precisely the definition of conditional mutual information. You simply is the averaging of a mutual information with respect to for fixed conditioning variable, and then basically averaging with respect to the conditioning variable. So this means that we have redefined these things, and so now what at the end what we can simply redefine new random variables. X1 is x1q, x2 is x2q, and y is yq, and therefore we end up with this set of inequalities, which is obtained by letting n going to infinity. And if n going to infinity, then all these bounds here, they vanish. So at the end, we get the inequalities. Okay, and this, of course, is for some distribution of this form, because we have constructed the problem to end up in this way, but we have no control on this distribution. So that's why the region is for some distribution. But in fact, our statement of the theorem says that any rate, we take the union over all possible such distributions, and so this, in fact, is the same region. So, to conclude the proof, now you see there is a glitch in this proof. The glitch is that we have introduced this random variable uniform over 1 to n, but then we let n go to infinity. And so this is really not nice, because it means that we do not know how large is the cardinality of the alphabet of this Q. So what we have to prove at the end is the cardinality bound. So in other words, the cardinality bound goes as follows. Even if we have proven a set of inequalities for a family of distributions where this Q is completely out of control, we don't know what alphabet is, because we have constructed it to take values in an infinite alphabet. It turns out that this region can also be achieved if I limit the alphabet of Q to be at most 3. So this is an important point. It's called, we have to prove a cardinality bound. I mean, you have a certain convex region, okay? And this convex region is obtained by taking a convex hull of a determined number of points. And then it turns out that, you can take the convex hull by basically averaging with respect to only a few of these points. And these, we will see that the theorem that I have mentioned a long time ago in this course, called the Carathodory theorem, plays a very fundamental role here. This is a result that uses properties of convex sets and convex hulls, and we are going to see how to a general technique to prove this type of cardinality bounds in the appendix of this chapter. So at the moment we just say, okay, it can be proved. Okay, we are happy about the fact that this can be proved. We are going to see more details in the appendix because it's interesting. To be honest, is very for specialists. So I don't think that most of you, unless you make a PhD on information theory, you will have to prove a cardinality bound in your life. But it's interesting to see how these things work because it somehow gives substance to this result. So at this, so we postpone the proof of cardinality bounds to later. So we stop here, and then we will talk about the special case where the channel, the multi-axis channel is Gaussian, which is more related to, say, again, physical channels that we use every day in wireless communications, for example.